Now, we want to look at what we call partial fractions, and it's the idea here of getting a fraction that is already in a simplified form and breaking it up into its unsimplified form where it's in we've got the common denominator and we're broken it back to where it didn't have common denominator. So that's the idea of of partial fractions, to break them back and work backwards basically from the idea of getting a common denominator. Now the idea why we want to do this is for a simple fact that it's going to help solve some integration problems. We couldn't just integrate that by itself. Even if we expand it out, we wouldn't be able to work it, have a rule or any way of doing integration of that function there. The way we have to do it is to break it down into the two factors here as denominators, separated and in separate terms, and then find out what the numbers would be up here. Now, because it's a number up there, and that's why we got the A and the B. And the idea too is that we're going to break it down into two linear denominators. So if it's going to be a fraction there, then it can't be a linear expression in the denominator here. It has to be one where it is of a degree less than a linear function, and that can only be a constant. So that's why we just put a constant a over x minus 1 and a constant b over x minus 2. It has to be able to break down to that. So, and our key is to try and find what a and what b will be here. Now, how do we do that? Well, we've got an expression here. We want to write it in this way. So these are equivalent expressions. Now, the way we do it, well, we take our right hand side and put it back into the form of a number over the product of the common denominators there. So to do that, we get a common denominator for x minus 1 times x minus 2, so multiply by a by x minus 2, and b would be multiplied by the x minus 1, like we would normally do a expression, an answer for simplifying those two addition of fractions. So now the idea here is that the numerators for this part and this part here would have to be the same. So that's why we've set it up like that. Now in this case, like, we've got 1, but that could be written as 0 times x plus 1. So if we're going to have a similar expression, then if I multiply the a by the x and the a and the b plus times the x, we can collect our terms in x. We collect our constants, and we can then equate these expressions, because 0x must be equal to a plus bx. So a plus b would have to be equal to 0, and minus 2a minus b would have to be equal to 1. So we've got two simultaneous equations, and we just need to solve it. If a plus b is equal to 0, then a would equal minus b. So what we're going to do is take our minus b and substitute a for it over here. And we get minus a is equal to 1. So a would be minus 1. If a is equal to minus 1, then b would have to be equal to 1. And our fraction can be expressed in that form. Minus 1 over x minus 1 plus 1 over x minus 2. So you can see how we got back to that. Now, when we get to this point, we can integrate both those. They just integrate to nice simple log functions. So it's not a hard integration once we get there. The hard part is getting from that point with partial fractions to get back there. Let's have a look at another example. X plus 2 on x minus 1, x plus 2, so x minus 2. So our two fractions would be x minus 1 and x minus 2 there. So again, we'd have to have just two constants on top. Expand it out, get our numerators and equate them like we did before. A plus b times x would be equal to 1, because there's 1x, and minus 2a minus b would be equal to 2. So we can set that up there. So we can do our substitution. A plus b is equal to, a would equal 1, so b was equal 1 minus a, and do the substitution. We work out what a is, and then we can easily work out what b is, and then we can get it back into this form as we need. Again, it's going to be very easy to integrate it. So x squared plus 2 over x minus 1, x minus 2. Now this one is a little bit different, because I can't just go and break this one up, for the simple fact is that this is not in its most simplified form. We can't do partial fractions if the degree of the numerator is equal or greater than the degree of the denominator. The denominator has to be of a greater degree than the numerator. In this case, x squared is the degree of x squared on the numerator and the degree of x squared in the denominator. So degree of 2 can't happen. So what we've got to do, if we can do that, well, when our degrees are the same, we can do division. So what we've done is taken our numerator divided by a denominator, so you expand it out. So you can get that. That will go in once, and then because I haven't done the polynomial division here, but it'll go in once with a remainder of 3x. So you have to do that polynomial division first. Once we're at that point, now the 3x there is of a lesser degree than the x minus 1, x minus 2. We can go back to this form. So we can split it up to the a on x minus 1, b on x minus 2. So it can't happen if we have the same degree, but it can when the degree of the numerator is less than the degree of the denominator. So we're just going to keep the 1 out the front as well. So that makes no difference. Notice we just keeps the 1 out the front because it's 1 plus the sum of those two fractions. So again, we multiply these two to give us the x minus 1, x minus 2. The a multiplies by the x minus 2 and the b multiplies by x minus 1. And that'd be equivalent to the 3x there. We rearrange so we can get in terms of x and the a and b with the x and our constants. So a plus b would equal 3 and minus 2a minus b is equal to 0. We can start to manipulate to get one term in one pronumeral in terms of the other, and then do the substitution. We calculate that b is equal to 6 and a would be equal to minus 3. So a little bit different. Degrees, if they're the same, do your polynomial division first, or you can decompose it, whichever is easier for you, and then get that to the point where you've got the degree less than if the numerator less than the degree of the denominator, and then you can do partial fractions. This one, not a problem, linear function on a quadratic. The problem is we want to get our quadratic in a nice factorized form here. So just a little bit different problem, but then we can break it back and get it into that form, and then we can cross multiply to get the a times x minus 4, b times x minus 3 would be equal to the numerator up here. And again, collect our terms in x and collect the constants, and then we're able to equate the two. 2 must be equal to a plus b, and the 3 would be equal to minus 4a minus 3b. We're able to do a substitution. We're substituting the a's in for the b there, and we're able to get down to a is equal to minus 9, b is equal to 11. So again, you can see how that works out. A little bit of extra work done, only because we need to get it into a nice linear factors so we can do the derivative there. And you can see this one. You might be thinking, well, wait on, could I play around and get a situation where I might be able to get a log function? If I'm going to differentiate, you might be able to do that, but you can also get it into that form as well. So we'll have a look at problems later on where it's 1 degree less than in the numerator than the denominator, and we can start to look at log functions there. And that's the aim a lot of the times. This time, x to the power of 3 and x squared. Well, the numerator is definitely larger than has a larger degree than the denominator, so we do our division. So x squared minus plus x goes into x cubed plus 5x minus 1 times, plus a remainder of x plus 5 on x squared plus x. So we can see that that's okay. It's derivative, the denominator is smaller than the degree of the numerator is smaller than the denominator. I can put that part here into a partial fraction. So that's okay. So that would be x. We could have that as x outside of x plus 1. So that's where our two fractions come from there. And then we've got the a on it and b on x plus 1. Again, multiply across, make it equivalent to the two denominators. And then we get a plus b is equal to 1. And from that, well, a would just be equal to 5. From that. So because a is equal to 1 minus b, do the substitution, b is equal to 5 would equal b minus 1. We can substitute in there, and we were able to work that out. Because the a was just a times the 1, so it's equal to the constant, so the constant's a. and A must be 5 then. So there we go. There's a few ways of doing some partial fractions. We're going to, in the next video, we'll have a look at some other things we need to consider with partial fractions. And again, remember, our aim here is to be able to look at all these ones and be able to integrate these ones in the end and get down to, that would come down to an expression like that where we can start to integrate all of those 4 expressions.